right, now we're going to look at a backward difference method. Okay, it can also be called the backward Euler method. And where I was calling the forward difference method or forward Euler an explicit sort of solution, here we're going to call this an implicit solution because what's going to happen is we're going to actually get a coupled system of algebraic equations that we have to solve. So here, the idea, the backward difference and so forth. So, you know, again, we're looking at u sub t equals alpha squared u sub xx. Now, in this case, when I do my difference here, okay, it'll look the same on the left-hand side. I'm going to have u sub j plus 1, comma, I, okay, minus u sub j, I, divided by rk. Okay, so I'm going up one time step. Now, the difference here is that I'm going to say that this is alpha squared, and instead of using values that I know at u sub j, that time, you know, so again, we start out with an initial condition. So I know, you know, u sub 0, so I could get u sub 1 and so forth from that. I am going to here use the forward time. So I'm going to say this is u sub j plus 1, I minus 1, minus 2 u sub j plus 1, I, and then plus u sub j plus 1, I plus 1, all over h squared. But you see, I don't know these. They're what I'm solving for. Okay, I do know this one. Okay, but I don't know any of the others. Well, so what we do, again, we do that same sort of thing. I'm going to make this, h squared over alpha squared k times u sub j plus 1, I minus u sub j, I, like that, equals u sub j plus 1, I minus 1, minus 2 u sub j plus 1, I, plus u sub j plus 1, I plus 1, like that. And now, if I move everything I don't know to the left-hand side and everything I do know to the right-hand side, what we get is minus u sub j plus 1, I minus 1, plus, and we're going to have the h squared over alpha squared k plus 2, okay, because I've got that term and I've got that term. I'll get a plus 2 from this one, and I'll have the h squared and so forth times the other. So u j plus 1 I, and then minus u j plus 1 I plus 1, And that's all equal to h squared over alpha squared k u sub j comma I. So see, I know this side. Okay, but I don't know any of these. And so you see here I've got an equation, but I've got three unknowns. Okay, but if I do this for, remember, you know, there's 0, there's 1. You know, so this is x sub 0, here's x sub 1, x sub 2, and we'll call this x sub n down here. You know, so if I do this at each of these points here, again, I know the boundaries. If I do these at each of the points, I can either set it up, either using the boundaries, I can do a system there where I, you know, because I still need to know u here, but I actually know what it is, but I can set that up as a very explicit equation. That'd be fine. But you see, then depending on how you want to, I either have n plus 1 or n minus 1 unknowns. You know, it's just, don't want to call these unknowns at the end, even though I do know them. I can and so forth. But I will get the right number of equations. Okay, so I will have, and again, now the way I do it as the n plus 1. I will have n plus 1 equations and n plus 1 unknowns. And they're linear. So these are linear equations in the u sub j plus 1 and i's and so forth. So I can solve this. Okay, and that's what it entails. If you do a backward difference, you end up with a big matrix equation. So it's a nice linear algebra thing. You'll have, and depending on your boundary conditions, how they're set up, you may get something that if you looked at the coefficients, it would look something like 1, 0, 0. These would all be zeros. And then I would have, you know, looking here at these equations, I would have a negative 1 and then a h squared over alpha squared k plus 2 there, and a negative 1 there, and zeros again the rest of the way, and then I'd have a 0 and I have a negative 1. And so you get a very structured system of equations. H squared over alpha squared k plus 2, plus 2 up here like that, and then a minus 1, and then zeros the rest of the way, and those non-zero coefficients will go just down like that. We call this a tri-diagonal system. And they can be very, very efficient to solve. And so we end up with a very nice system of equations. Okay, and you know, but this is an implicit method because you see most of what I'm working with here in the equation I don't know, and so I get these implicitly defined by the previous stuff. And so this is either the backward difference or backward Euler method. And this is our what we would call an implicit solution instead of an explicit solution. Okay, so that's a backward difference. That's not what we're going to implement. And we'll talk about why in the next video.